Okay, students, can you see my slides? Someone?
Yes, sir.
Okay. All right, let's just continue. Others will keep on joining, no problem. So we stopped somewhere here and we were talking about the Miller indices, where basically how we define a crystal. Okay, and we did mention about how we can define planes and how we can define directions. And the directions with the same Miller indices will be vertical or perpendicular to the planes. That means the plane which is 0, 0, 1, the direction perpendicular to that plane is 0, 0, 1. Okay, the same values, right? If you remember that. So we did these calculations here of Miller indices. So let's continue. So like I say, the planes are defined by the Miller indices. Okay, and so we say the Miller index reciprocals of the intercepts. Okay, that means where the plane cuts the particular axis, right? So like this one, you see here, if we consider this as 1, this plane cuts, suppose the x-axis at 1, the y-axis at 1, and the z-axis, or here we are talking about the c-axis, it does not cut at all, right? It is perpendicularly going up. That means we have to say that it cuts this axis at infinity. It does not cut at all, right? So it is at infinity. So if you take the reciprocal, it is 1 by 1, 1 by 1, and 1 by infinity for this one. So 1 by infinity becomes 0, and 1 by 1 is 1, 1 by 1 is 1. So that's the Miller indices 1 by 1, 1, 0, and that plane, we call it as the 1, 1, 0 plane. All right, so any other planes parallel to this one, if you can continue drawing more subplanes this way, that way, everywhere parallel to this one, then all of them will be clubbed under the family of 110 planes. Now look at this one. So here you see, so it is, this is the plane. All right, it's on the axis, so it does not cut. All right, so you see it's going parallel to this one. All right, so if you assume that it is here at this point cutting, all right, the x-axis at 1, the other ones, the y and the b and the c, that means here it will not cut anywhere, so it's going to infinity. Okay, and that's why the Miller indices will be 1, 1 by infinity, 1 by infinity. Okay, and so these are all planes from a simple cubic structure. Okay, we had already seen the simple cubic structure where the atoms are at the corners. So these are basically the different corners which we are trying to connect, right? And that means we can slice a cube. Let me pick up this is suppose a simple cubic structure. We can slice it any way we want, right? We can slice it this way, we can slice it this way. It's just slicing across a piece of cheese. Suppose you have these cheese cubes, right? You take a sharp knife and you cut any way you want. You are cutting a plane. That means the moment you cut across the flat surface that will be exposed, that is a plane. Okay, so you can cut through any point you want. You will get a set of planes. So there are infinite number of planes. But then when you're talking about a single, say a unit cell, then of course we are talking about planes that cuts through atoms. So when you're cutting a plane, it has to pass through an atom. Okay, so this is another one again from the simple cubic, and here it is, see, it is cutting at 1, 1, and 1. All right, on all the three axes. This is 1, this is 1, this is 1, and that's why it will be 1 by 1, 1 by 1, and 1 by 1, which will give you 1, 1, and 1. Okay, so this plane is the 1, 1, 1 plane of the simple cubic structure. Okay, that's how we describe it. It's not very difficult. So you see here now, this particular plane, right? This particular plane, all these planes are spaced. Say, suppose we say, when we talk about anyone, we say, suppose this is the origin of the scaling system, and we say this is 0 0 0, right? For all of these we say this is 0 0 0. Then what happens is all of these planes, all right, say this one and this one, they fall in the same one. You see, it's just a translation. This one and this one is just moving. These are parallel planes, right? So both of them, if we take the Miller indices and we reduce it to the minimum integer, it will come out to be 1 0 0. That means this plane is also 1 0 0. This plane is also 1 0 0. So this and this plane fall in the same family. Similarly, this plane and this plane, they have the same Miller indices 0 0 1. Okay, they fall in the same family of planes. Okay, similarly this and the back one, this, they fall in 0 1 0. Okay, so this is how we go, and they all behave same. They all the spacing between the atoms will be same, right? But doesn't necessarily have to be that, you know, the 100 planes and the 1001 planes does not necessarily have to be the same. I mean, as far as the spacing of the atoms are concerned, here for the symbol cubic it will be same, okay, because all the edges are of same length because it's a cube. But for other crystal structures, the 100 planes have separate spacings as compared to the 001 planes. Okay, so that's how we classify them into different families. So it's this one connecting the corners, going as a sort of like a diagonal type of thing. The same. So this and this, the first two are in the family of 110. Second and the third, they fall in the 011, and these two fall in the 101 plane. Okay, if you do the simple calculations, you know, like you consider this point to be 0 0 0, and then you just check out where this plane cuts the different axes, then you can calculate out and you'll find that finally you can reduce it down to 101. That means it can be some integral multiples of 101. Okay, are there any students waiting outside? No, no, all are in. Okay, so it's fun cutting around crystals. So if you try, you'll see that you can do the calculations of the Miller indices, right? So you see, again, this is just to show how it translates out. So this is a simple cubic structure. That means this is the unit cell, and we can build it up like this. We are simply adding more unit cells. We can take it up also, we can take it down also, we can take it out of the screen towards us also. So it can be in all directions, okay? No matter what, all these planes that are parallel, they fall in the same family, all right? So here it is a 100 family, right? So similarly, these are just examples I'm showing, okay? So it's the same. They're all in the same planes, and the atoms are exactly the same in a family of planes. I mean, no matter whichever is the plane, the atoms that are placed here will be exactly the same, okay? Again, this is another set, the 111 plane, okay? It cuts through the crystal, okay? This is the 111 plane, this is another 111 plane. So these are all parallel to each other, and they all can be categorized under the 111 family of planes, okay? All right, now let's look at this small numerical. Says if a plane in a cubic structure, we are taking the simplest structure, that is a cubic structure. So it says if a plane in a cubic structure intersects the coordinate axis at half, half, and half, what kind of plane is it in terms of HKL, that means the Miller indices, and what does it look like in the unit cell? Okay, so if we try to draw this now, so you see here, this is your simple cubic structure, and we say that the plane that we are talking about cuts A at half. All right, so here is our A, it is cutting at half, B at half, and C at half, right? So this is our plane that we are talking about. So what kind of plane is it in terms of HKL, and what does it look like in a unit cell? All right, so we are saying half, half, half. All right, so here it is cutting A, B, and C at half, half, and half. So how do we calculate the Miller indices? We take the reciprocal. That means 1 by half, 1 by half, 1 by half will give you 2, 2, 2. All right. So this is the particular plane. But if we want to talk about the family of this plane, because then we have to reduce it to the minimum integer. And here we can nicely divide it by 2, all of them, to bring it down to 1. So if we say that it belongs to the family of 1, 1, 1. Okay. So that is the plane. So it is 1, 1, 1. Then we talk about the directions. I already told you before that the directions with the same value, like 1, 1, 1 direction will be the direction perpendicular to this plane. Okay, if you cut out this plane exactly perpendicular, making a 90-degree on the surface, the direction that is going out, that is the direction with 1, 1, 1. All right. So crystallographic directions are vectors. Okay, vectors means it has both direction as well as some value. All right. So are vectors that contain the components of the unit cell designated as something. You know, you say UVW, okay, that's a generic. Okay, these are variables. They are calculated by repositioning the directional vector through the origin. All right, that means from the 0, 0, 0 point and translating the projection in terms of the lattice constants A, B, and C. All right. So we consider the direction going through the origin, all right, and then the other point we determine through using values of A, B, and C. That means these are the points where the plane cuts the different axes. The values are then converted into the smallest integer values. Like before, we try to divide it and see how small we can make it. If D is the space between adjacent planes, that means the parallel planes, if the spacing between them is D, which is a lattice constant, okay, which is spacing between the planes means spacing between the atoms, then D is given by this value, okay, A by root over the sum of the squares of the Miller indices, A square plus K square plus L square, okay, this is the formula for the lattice spacing, we call it, all right. So let's look at this small problem now, numerical. Calculate the crystallographic direction of the ray. Suppose the ray is coming out, originating from the origin, that means the point 0, 0, 0, that is the origin, and passing through half, 1, and half. Okay, so we need to find out the direction. I mean, we need to give some number to this direction where the source is coming out from 0, 0, 0, and it is passing through half, 1, and half. All right. So basically, we need the difference between these. So half, 1, and half, and 0, 0, 0. We subtract this. So first one, half minus 0, 1 minus 0, and half minus 0. Okay. These are the points we're calculating. And then we get half, 1, and half as a direction. All right. So we need to convert it into a integral form. That means it cannot have a value like this, which is a ratio. So to remove that, we have to, the simplest way to do is multiply it by 2. So if you're multiplying 1 by 2, we have to multiply all by 2, right? That's what we are doing, multiplying by 2 all of these three. So 2 cancels out. For the first one, we are getting 1. 1 into 2 will give you 2. And again, 2 cancels out, we are getting 1. So this is the value, or you can say this is the numerical value of the direction where we are talking about, that is the source is from 0, 0, 0, and the ray is passing through half, 1, and half. Then its value is given by 1, 2, 1 within square brackets. For directions, we use square brackets. Now suppose we are giving another point now. Suppose minus 2 by 3, 1, and 1 by 3. All right. Then again, we do the same thing. Since we are considering the source to be at 0, 0, 0, we simply deduct 0, 0, 0. So basically take the same values, because deducting the 0 means it makes no difference. We still have minus 2 by 3, 1, and 1 by 3. Again, now this is not in an integral form. So how to do that? We multiply by 3. All right. We multiply by 3, and then what we get, 3 and 3 will cancel out. We have -2 here, and then we will have 3 here, and again 3 will cancel out with 3. We have 1 here. So it's -2, 1, and 1. And when we are putting it like for planes and directions, we put the minus over it. So it's 2 bar. We write it as 2 bar. So it's 2 bar, 3, and 1. So these values give the directional values of a ray moving out from 0, 0, 0 and passing through this point -2, 1, 3. All right. So if you say that, if I say asked to say draw the ray with Wheeler indices of 2 bar, 3, and 1, then you will simply have to draw one starting from 0, 0, 0 and passing through these points. All right. Then this is given by this value. Okay. So let's try another small problem. So what are the directions of the following vectors defined by the following lattice points? All right, the points are given. So basically the arrow, that means the vector, which is the direction, will start from 0, 0, 0 and end up at the second one. That means 0, 0, 0 it starts and ends up at 1, 0, 0. This one starts at 0, 0, 0 and ends up at 1, 1, 1, 0, 0, 0 and 0. And that way we have to find the directional values, right? So this is the simple cubic structure, and we are talking about taking this as the origin. This is the 0, 0, 0 point from where all these vectors are coming out, right? That's what we said, from 0, 0, 0 all the vectors are coming out. So first vector will go through 1, 0, 0. This is the vector going through 1, 0, 0. Similarly, the second vector goes through 1, 1, 1. That is the second one, goes through 1, 1, 1. The third one goes through 0, 1, 0. This is the third one. And this is the fourth one going through 1, 1, 0. All right. So we know this. This is 0, 0, 0. So how do we define this one in terms of a value? All right. So for A, all right, it is directly here going this way from 0, 0, 0 to 1, 0, 0. So we use 1, 0, 0 minus 0, 0, 0. That will give us 1, 0, 0, right? So that is A, because this is A. A is this length. That means we are talking about the length of this one now. All right. So it is A. So this is also A, right? This is also A. That means if I talk about the 0, 1, 0, there also, see, 0, 1, 0 will also be equal to A, because we know all the sides of the cube, they are A. So this is one side of the cube, this is another side of the cube, so they are A. But talk about this one now. This is not a edge of the cube, right? So to get this one, we can use Pythagoras theorem, and we say A square plus A square will be this square, right? So that's why when we're talking about 1, 1, 0, this one, you see, we are saying root over, because this will be squared. So since it's one value, we are putting the root over here, a square plus b square. This is the a axis, this is the b axis. We say a square plus b square. All right. Since a equal to b, so in place of b, we can write a again. So a square plus a square is root 2a square, or this one we can pull it out of the root. So a root 2. So this is for this one. All right. So that is the length of the vector. Similarly, for this one, how to find it out? We say it is this square plus this square. And this we already know as a square, a root 2, all right? Or we can say a square plus b square in general. So a square plus b square is for this one, and this one is c square, all right? So a square plus b square plus c square will give you this square, all right? So a square plus b square plus c square will give you b square, and for b is root over a square plus b square plus c square, and all our equal values can be considered as a. So a square plus a square plus a square will be root over 3a square, or a you can pull out, so a root 3. All right. So b vector length will be, or its dimension will be a root 3, and the directions correspond to orthogonal planes. All right. A 1, 0, 0. All right. So orthogonal planes, that means this is the direction and it is going out perpendicular to this plane, right? This particular plane, this vector is going out perpendicularly, correct? This vector is going out perpendicularly. So we will designate this as having the same value as this plane, okay? But only in a perpendicular direction. That's why this plane is 1, 0, 0 plane, okay? So 1, 0, 0 plane. So this vector direction is 1, 0, 0. Similarly, for B, all right, it will be 1, 1, 1. Okay, the plane that is through which that this one will be perpendicular. We could think about this. This will be perpendicular through this plane, right? It will be perpendicular through the 1, 1, 1 plane. All right. So it will be perpendicular to the 1, 1. This one will be perpendicular to the 1, 1, 1 plane, and that's why B is designated as 1, 1, 1. Similarly, C as 0, 1, 0, and D as 1, 1, 0. Okay, that's how we designate. All right. So if you're asked to do a small problem like this, you simply calculate out the length of the vectors and you find out whether these vertical vectors will be perpendicular to which planes, and accordingly you find out the Miller indices for the vectors. Okay, so uh, that much is enough for your crystallography, because this is not a course on crystallography. So when it comes to crystallography, we should always be aware of the Miller indices, because that's how we talk of the different planes. All right. So this much of knowledge on Miller indices is good enough. I will give you a note, of course, to read. All right. Okay. So that completes this set of slides. Okay. So what I'll do now is I'll pick up one topic that was from the synthesis part. Uh, I did not have a slide then, but I want to explain to you regarding what we call as stability of a colloid. I'll come to that because that is supposed to be the next lecture, but I didn't bring the slides today, so I'll put up on a new slide and just discuss with you. But before that, the next thing is that we need to have one more exam, okay, like last time, right? The second exam, we can have it as per our convenience. So I am just thinking that we can have it next week, if that is okay with you all. Maybe how about next Monday, 1 hour? I'll keep it short. Is it okay with everyone? Should be fine, I think. Or you have any other pressure?
Yes, sir.
Okay, good.
No, sir.
Good. So next Monday, so that you can study on Sunday. But believe me, the last exam was very, very simple. So I know everybody scored extremely well because it was so straightforward. The second one might be slightly difficult. Okay. Difficult in the sense that, I mean, I'm not saying difficult. It's like whatever we had been discussing, it will be based on that also. But then maybe you need to write a couple of points here instead of just selecting the answers. Okay. Like last time, I think I just gave 2 questions where you need to write. Maybe this time I'll give you a few more questions where you need to write a little bit. Okay. But I'm not saying write an essay, but it's not just selecting the answer, but putting in some thoughts from your own. Okay. So let's fix the exam on next Monday, which the date is 28. Okay, from 9 or 9:15, 9:15, let's keep it 9:15. 28, from 9:15 we will have a short exam through Google Form. Okay, so all of you come prepared and please inform your friends. I'll put it up in the group also, WhatsApp group also. Okay, so now let me discuss this one point. Let me pick up a new slide. Okay, let's pick up a blank slide. And let's talk a little bit about stabilization of colloids. All right. So you all know what is a colloid. If you remember, I was saying that it's a liquid where some small particles are suspended. That means they are moving around in random Brownian motion, but they are not settling down with gravity, and they are moving around and making the liquid homogeneous. And a typical example I gave you, if you remember, was milk. Milk is a colloid, okay? So it has a lot of particles suspended in it, and in a normal condition, we see it as a homogeneous liquid because milk is white, like no matter how many spoons of milk you take out from a glass, every time you're taking out the same thing, no, it's not different, correct? You cannot separate out the ingredients from it. You cannot separate it out with your eyes or with your taste, all right? It's there. It's like a composite solution. So that means it is a very stable colloid. Okay, so milk is a stable colloid. So that means stable in the sense that whatever is there will remain as it is. That means if you have particles of 1 nanometer of a certain material, then it will remain as 1 nanometer. If it continues at a state, then it is a stable colloid, right? And if you remember, I even told you how we make cottage cheese or paneer. So what we do, to the milk, we put some lime or vinegar, okay? And then all of a sudden, what happens? The white stuff settles down at the bottom, right? And we have a sort of like a transparent liquid on the top. That means all those small particles that were moving around in Brownian motion, they were not being affected by gravity. All of a sudden, they started coming together, then becoming heavier, and then they were settling down, right? So they sort of moved out from a liquid phase to a solid phase. So what has happened? Okay? The reason for this is what we call as destabilization of the colloid. That means a stable colloid can be made to go unstable, and the moment it is unstable, it won't retain the original properties. Okay, so just by adding lime, we somehow made the milk unstable. All right, and then the moment we made it unstable, things started to agglomerate. So started to become bigger. They came together, and then they settled down because they became heavy. Right? So what is it that happened when we added the acid, I mean the lemon juice, all right, or the vinegar? So what was happening, you see here, what was happening was, say suppose, let me quickly draw. Suppose this is a container of milk, all right, and there we put in some small nanoparticles, all right. We put in some small nanoparticles and we put a different color. Say fill y, say suppose this is a nanoparticle, okay, inside, I mean, the jar, right? So we have so many of them, all right, so many of them moving around here and there, right? Billions of them may be moving around, but the situation is like that, that no matter how much they are moving around in random motion, they are not coming together, all right? So they are still retaining their original size and shape. That means this is your stable milk, right? This is your stable milk, right? Now what happened? To here we added we added some lime. Fine. Where is the color? Okay. So here we added some lime, right? So we added some lime. All right. So lime is basically acidic. You know that, right? So it is acidic, means the moment we are putting it, there's an increase in the hydrogen ion concentration. Okay, there will be more hydrogen ions being released. Now, how are all these particles that were there separated from each other? They're separated because when they are in the liquid, what is happening is there is a large number of charges sitting on, on the particles. All right, there are a large number of charges. How can I put a positive charge? Is there something like this? Yeah. All right. Okay, but this is too big. So, but you can assume that there are a lot of. Let me make this bigger. Let me pull it out to explain. All right. All right. So this is an enlarged version of the nanoparticle, and we have so many of these charges sitting on the surface. All right. So you will have charges like this sitting on the surface. There will be a lot of charges available from various things that are present inside the liquid, and these end up as in the form of some atoms with charges. All right. So those atoms with charges actually start sitting up on the surface of the nanoparticles. Okay, it's a sphere, and these particle charges are sitting all over. These charges may be positive, these charges may be negative. All right, depending upon what type of nanoparticle we are talking about. Fine. So automatically what is it? We'll have a lot of, and it's definitely, I just drew one layer. It will be not only one layer, maybe 3 or 4 layers of these positive charges. All right, and so if I say this is one nanoparticle, then we have similarly another nanoparticle somewhere nearby. All right, another particle. So all these particles are moving around in random motion inside, and naturally they cannot come very close together because the positive charges, for this case let's draw a positive charge, maybe negative also, but whatever the like charges, they're same charges, right? So what will happen, there will be natural tendency to repel each other. All right, so there will be a natural tendency to repel each other, and let's draw this. So there will be general tendency to repel each other. All right, so let me put some color. So there will be a tendency to repel. All right, so between these and between these maybe. So if I draw another one, Control CV. All right, let me pull this a bit down. All right, so there will be repulsion. So there will be mutual repulsion because of the available charges. Okay, so the number of charges sitting on one individual atom, one individual nanoparticle will be the same as another individual nanoparticle. The overall charges, if you can find a value for them, will be the same, right? And so they will naturally keep on repelling each other, and the chances of them colliding and I could say agglomerating is minimal. It does not happen, and that's why this is a stable milk. Now we added lime. Suppose this is the case before the lime. The moment we added lime, we are putting a lot more positive charges here from the hydrogen that is coming in, H plus, right? So a lot more positive charges come in, and automatically what happens, the overall neutral condition, because the number of positive charges are adjusted by the number of negative charges here. That means if there are X number of charges inside this one, charges may be sitting here or maybe moving around also, but whatever, the number of positive charges is the same to the number of negative charges present here, and that's why a stable colloid is always charge free, it's neutral. All right, now what we are doing, we are adding some more charges. All right, we are adding some more charges, then automatically what will happen? The number of positive charges will be more than the number of negative charges. Suppose one of the charges will be more than the other, and then they cannot retain that electrostatic stabilization. I mean, the repelling of the charges or the attraction of the charges, that becomes sort of affected, and then it cannot retain that mutual separation. And sometimes what happens, because of this change, these particles, they cannot retain the charges as they want to, or with everyone having the same charges, doesn't happen. And then what will happen, we say that they start colliding, they start coming together. All right, and that is what is called as an unstable colloid now. So if the charges are not balanced inside a colloid, now this is a typical example. It does not happen for every colloid. Okay, this is one example I'm giving you because I talked about milk. All right, so what happens then? They start agglomerating, and then all this white stuff, they will come together. All right, they will come together, and then what will happen? They will all settle down, because now gravity will start having an effect on them, and because they are going into the macro scale. All right, so they will all start agglomerating, coming together, and then because of the effect of gravity, all of them will actually settle down. All right, all will settle down at the bottom. All right, and then we are getting what we call as, we are getting cottage cheese, right? Cottage cheese, or in our own words, it is paneer. Fine. So we are making paneer that way. The same thing happens with our artificially synthesized nanoparticles also. So this type of stabilization that is happening here because of the presence of charges on the nanoparticles, this type of stabilization is called electrostatic stabilization. All right, so we call it electrostatic stabilization because of the electrostatic charges that result in the stabilization. Right, now we can actually calculate the value of these charges. All right, so that value that we talk about, so that is, we have just 5 minutes, so let me then not talk about the charges now. I will come to the charges, but let me mention the name. It is called zeta potential. I'll explain zeta potential in the next class. We have next class tomorrow, right? So we'll talk about zeta potential tomorrow. All right. So now let's just talk about stabilization. So I said the moment that we have charges like this, then we call it as a, if it is stabilized, we say this is because of electrostatic stabilization. Now, apart from that, if the charges are not sufficient or there are no charges at all, then the particles will not be stable. So the moment we make these particles, leave them, immediately they will all come together and settle down. All right. So let me pull in another slide. So then what we do, if our particles, you know, if our particles do not have requisite charges on them, right? Then how can we ensure that they do not collide and merge together and become bigger? We need to retain their sizes. So then what do we do? Sometimes what we do is we cover the particle. All right, we cover the particle. Let me just make it. We cover the particle with a layer of a polymer. Okay, let me just put a different color on this one. Let me put a different color. All right, suppose this color, let me send it back. See, if we do something like this, that the original nanoparticle, we cover it with a different material, say a polymer. Polymers are, long chain molecules, and since they're long, it's very easy to use them as cover. All right, that means we cover the nanoparticles with some other molecules like this. All right, and all of them. Okay, that means next our particles will look something like this. All right, will look something like this. All right, will move around something like this. All right. Just showing a few. All right, then these will not remain. So we are now covering all of them with a cover. Okay, it's just a cover that we put on. Okay, so if we have a cover that we put on, anyway, let's forget all. Let's just look at these three. Let me just delete this. So now what happens? They automatically, anyway, they will keep on colliding like before. They will still collide, but because of the presence of these polymers, normally they are very long chain, and they are also like what you can say elastic in nature. That means the moment they hit, it's like now we are making them into balloons. All right, our rubber balloons. If we hit the balloon together, they just move away, right? After colliding, that means this one coming here will collide with this one, and because of the elasticity of the capping, we call it capping, they will move away. All right, they will move away and they will not agglomerate, and then your colloid will become stable. All right. So if that happens, that means we make particles like this with a covering that does not allow you to come together and agglomerate, and the particles are stable and the colloid is stable, then this type of stabilization in a colloid, we call it that steric stabilization. Okay, so the moment we put some covering on top, then the stabilization process is called steric stabilization. Now, what happens is sometimes these polymers that we are using to cap our nanoparticles, they can also be made charged. All right, we can make them positive or negative. Normally, can make them positively charged. We can do that. All right, we call so either protonation or deprotonation. We can make